Okay, welcome to another Programming in ARM Assembly video series. And in this series, I want to expand our toolkit. So up to this point, we have so far created a general purpose print function, and I've got a video on that. And we've created a general purpose A to I function, and I have a video series on that. So now I want to go the other way around. I want to go integer to ASCII. And once again, I've actually already recorded this video series, but I wasn't happy with it. So I'm going to redo the entire recording. But that does mean that I've already learned quite a few things, and I've created a roadmap for myself to be able to follow. So the advantages of doing the re-recording is that since I've already gone through the whole process, I know what to do. The disadvantage potentially is that you won't get to follow along with some of the problems that I faced when I was going through it the first time. So I'm not sure which method people would prefer, if they prefer just kind of seeing the version where I've kind of already struggled and figured it out and we can just kind of present the information cleanly, or if you'd like to follow along and see all those struggles as I went. So let me know what you think on that. Leave your comments down below. But let's go ahead and get started here. So we'll start as usual with a mostly empty directory, but we're not going to reinvent the wheel. So I'm going to be including the print.s function that I've already created. I've already got a video on that. And I'm going to be including the A to I function that I've already created, and I've already got a video series on that. I'm not necessarily sure which of these we'll end up using, but we will have them here as part of our toolkit just in case we need them. So let's look at our makefile. So our makefile has the main.s, which we haven't created yet, has the print.s, which was already done. We have the A to I.s, which is already done. And then we have the I to A.s, which is what we're going to be creating here. As always, the main.s is just going to serve as a wrapper function, a driver, so that we can drive the I to A function. So the main.s will just be serving to pass information in and receiving information back from I to A. Otherwise, we're just going to link everything together when we're done, delete our .o files, and then that will be our makefile. Okay, so let's edit our main.s, and as always, we're just going to start with a .global label. We can point, we'll have the .global label point to the underscore start, which is the default required by the linker. Can change it if we want to, but I don't feel the need to change that start label, so I won't. So we'll create, that will be where the start label will exist. Then we'll have our exit label, and in order to get out of the program, we need to move into register 0 and exit code of some kind. For now, we'll just assume a normal exit, so we'll use the immediate value of 0, and we need to move into register 7, the immediate value 1, and we need to do a service call of 0, and then we will have the .end directive at the end of the program, not required by the linker, but I do like to have it there. And it's safe to assume that we're going to need some data, which means we're also going to need this .text section in order to tell the assembler and the linker where our actual code begins. So let's go ahead and write that out and quit. And let's write the foundation for our I to A code as well. So we'll have the .global label at the top. We'll have the I to A label that we'll call into to tell the linker where we want to begin our code at, which is right here. And we'll also want to exit out of this function at some point, so we'll create an exit label, and we'll have the .end directive. So let me go ahead and write that out, and with that we should have everything we need to be able to test our makefile, test the assembler, test the linker. So let's try that with the make. No issues there. So if everything is currently working correctly, we should get an exit code of 0, and we do. Alright, so before we jump into the program, let me zoom in on this document that I've created. And so first of all, I always have the system call reference available to me because I can't memorize all this stuff, and even if I do, it's good to refer back to it. And then what I have down here is just, it's this system call reference, but explained or outlined in terms that make a little bit more sense for specifically for ARM assembly programming. And then down here, I've just got a section to remind myself how to take input from the keyboard when needed. I'm not sure if we're going to need that for this go around. Have our ASCII table so that we can look up these conversions. So at the moment we're doing integer to ASCII, so primarily we're looking at this like 0 through 9 section over here, the character 0 through 9, and how character 0 is 48, character 1 is 49 in decimal, and so on and so on. And 0 in hex would be 31, and hex would be 31, but for the most part, I use the decimal column. I'm just more comfortable thinking in terms of decimal. So let's think about what we need to do to convert a value from an integer into its ASCII equivalent. Essentially, let's use the number 1, 2, 3, 4 as an example. But the bottom line is we need to isolate this number, and this number, because when we go from an integer to ASCII, it loses the context of 1,234. What we really need is a string at that point. We basically need this string of 1,234. And as a string, it's not, we think of it as 1,234, but in terms of a string, it's really just the ASCII value 49, the ASCII value 50, the ASCII value 51, and so on. So a way that we can convert this is to just by using powers of 10 and division in order to break out each individual number. So let's take 1, 2, 3, 4, divide by 1,000 because that's the highest power of 10 that we need. And when we divide that by 1,000, we end up with the whole number 1. Now, of course, technically, if we were doing this on pencil and paper, it would be 1.234. But for our purposes, we're only interested in the whole number. So when we divide an integer by an integer, we get an integer. We don't get a floating point. So when we take this, we're going to get 1. And then I want to take the original number, 1,234, and I want to subtract 1,000 from it so that I'm left with, because I've already isolated the 1 at this point, so I don't care about the 1 anymore. So when I subtract 1,000 from that number, I'm left with 234. And then I can basically repeat the process with the next lower power of 10. So I can take 234, divide by 100, which gives me the whole number 2. And then I can take 234, and I want to subtract off of it 100, but not just 100, because if I subtract just 100, I'll end up with 134. So I actually want to subtract off 100 times whatever the result of that division was. And that's actually what I'm doing up here as well. It's just not as important to point it out because 1,000 times 1 is still 1,000. But if this were 7,234, then it would be important because we want to multiply 1,000 times 7 so that when we did the subtraction, we would still end up with 234. So anyway, after we complete this operation, we step down another power of 10, and we take 34, we divide by 10, which gives us the whole number 3. Then we take the 34, we subtract off 10 times 3, which is 30, and we're left with 4. So by doing this process, we've isolated the 1, we've isolated the 2, we've isolated the 3, and finally we've isolated the 4. Okay, now this is, or I guess the next thing I should say is we can look at this number and we can see just by eyeballing it that essentially the highest power here is 1,000. And if this number were 12,340, we would know that the highest multiple of 10 power would be 10,000 and so on. But obviously the computer has no way to know this, and we don't want to make any assumptions from the start because we don't know when we go into our function, we don't know, are we dealing with the number 1, the number 12, the number 27, the number 150, the number 10,628, we don't know. So in order to calculate, or in order to figure this part out, where does this highest power of 10 multiplier come from, what we can do for that is we'll start off by, we'll have some register that will initialize to the immediate value of 1. And then we'll take our original number and we're going to divide the original number by 10. And when we do that, we're going to end up with like 123 in this case. Again, it would technically be 123.4, but we're throwing away the decimal values. Once we've done that division, we now know, and we didn't end up with a 0, essentially. we want to take that register that was originally initialized to 1 and multiply it by 10, and then that's going to increase our power of 10 from the ones place to the tens place. And then we're going to go back into that loop, and now we're going to take 123, we're going to divide that by 10, which is going to give us, in this case, the whole number 12. Now we're going to take the power of 10, which earlier was 10, we're going to multiply that by 10, and we're going to have 100. So we've increased the power of 10 count again. And then we're going to do that again. We're going to take the result of that division, divide it again by 10. In this case, we're going to end up with the whole number 1. And then we're going to take that power of 10 from up here that we had, or the power of 10 multiplier, which is 100. We're going to multiply that by 10, and that will give us 1,000. And we'll actually do this part first. We'll calculate, how high up do we need to go, because potentially, our original number could be, 10. It could be into the tens thousands. It could be into the hundreds of thousands, millions, tens millions, all the way up to the possibility of a billion, because that would be the highest possibility for a 32-bit number. Okay, so that's going to be the idea. So we'll do this first, and then once we know what the highest power is, then we'll step into this part, and we'll be able to break out our individual numbers. And since I've already gone through and recorded this, I have learned a lot, so I've already created a roadmap so that I don't have to go through and struggle figuring all this out again. So let me just walk through the roadmap that we have, or that I've already created. So as always, at the start, we need to declare what the assumptions are for using this function, because whoever my future self, when I'm looking at this later, I need to know, well, what was I thinking 6 months ago, 6 years ago, whatever the case, when I built this. So right at the top, I'm saying that the assumption is that R0 will contain the integer. So if the integer is 123 or 4,556, whatever the integer is, R0 must contain that integer. And then R1 must contain a pointer to the memory address where we're going to store the result of the integer conversion. So remember, we take 123, we convert it into its ASCII values, and then we're going to store that result into R1. And then the output from this function is that R1 will contain the converted value. So the inputs are R0, R1, the output is R1. And then when we step into the actual code, what we're going to be doing is we're going to start off by saving and initializing our registers. So, we're going to use the push function to push registers, X through Y onto the stack, including the link register. And then we're going to move into register 2, an immediate value of 1. And this register is going to keep track of that power of 10 multiplier. So like I was going through in this part here, we initialize to 1. And then as we do the division, we go from 10, 100, 1,000, potentially 10,000, 100,000, a million, and so on. So this register will keep track of that power of 10 multiplier, and we'll initialize it to the ones place. And since we can't use the immediate value 10 inside of a multiplication or division operation, we're just going to put the immediate value of 10 into register 3. That's the only reason it's going to be there. If we could just use the immediate value 10 inside of the multiplication and division operations, we wouldn't need to do this. But since we can't, we're just keeping the power of 10 multiplier in register 3. And then R0 is going to contain the integer that we're going to be converting, but we're going to be messing with that number. So when we originally come in, we're going to make a backup copy of R0 so that once we go through our loop, we're going to end up messing up that original number. So we need to keep a copy of it so we can get back to that original number. So once we've done the initialization step, we're going to drop into a loop. And the first thing that we're going to do in the loop is we're going to compare register 4, which is our backup copy of our original number. We're going to work with the copy instead of the original. And we're going to compare register 4 with the power of 10. And we're going to say, is it greater than 10? If register 4 is greater than 10, we're going to divide register 4 by the power of 10, by R3. And also, if it's greater than 10, we're going to multiply R2 times the power of 10. This is the one that keeps track of our power of 10 multiplier. The first time we go through the loop, it'll be when we enter the loop, it'll be 1. And the first time we go through the loop, it'll be 10, 100, 1,000, 10,000, and so on. And then we're going to say if R4 was indeed greater than 10, then we're going to branch back to the top of the loop. Whenever this condition is not true, we're going to fall out of that loop and move on to the next part of our code. And that next part of our code is going to be to restore R4 back to its original number, because when we do this operation here, we're taking, for example, 1, 2, 3, 4. We're dividing it down to 1, 2, 3, dividing that down to 12, dividing that down to 1. So by the time we're done here, we will have lost the information for that number. So before we move on to the next part of the code, we're just bringing back that original number. And then we're going to fall into the next part of the code, which is the part that's going to do the first thing we talked about, which is this stuff up here. We're going to take our original number, and utilizing the power of 10 multiplier that we just figured out in the previous loop, we're then going to divide things down to isolate those individual numbers. So the first thing we're going to do is just, are we done yet? We're going to compare register 2 with the immediate value of 0. And if register 2 is less than or equal to 0, it means we've hit the null byte, or we've hit the carriage return or something like that. Well, actually, I guess it'd be the null byte. And then we're going to move down to this label, but we'll get to that later. First, we'll assume that we aren't done yet. So we're going to take register 5, and we're going to say register 5 is equal to register 4 divided by R2. And remember, register 4 is our original number, our 1, 2, 3, 4. And remember, register 2 was keeping track of our place value, our 1's place, our 10's place. So in the case of 1, 2, 3, 4, R2 will originally be 1,000. So we're saying take R4, original number, and divide it by 1,000. That's how we're going to isolate the 1 in the case of 1, 2, 3, 4. Then we're going to say set register 6 equal to R2 times R5. And remember, R2 at this point will be, it's our power of 10 multiplier. So in the case of 1, 2, 3, 4, it's going to be 1,000. And R5 will be equal to the value that we just divided out. So in the case of 1, 2, 3, 4, it'll be 1. So we're saying R6 is going to be equal to 1,000 times 1. So R6 in this case would be equal to 1,000. And then we're going to subtract. We're going to say R4, which was our number, is going to be equal to our number minus R6. So just to follow along here with that logic, we're doing this step right here. We're saying, we've calculated, we've isolated this number. So now we need to multiply that number that we just isolated times the current power of 10 multiplier that we were working with. And then we want to subtract that value from the original number so that we can work down by 1 power of 10. So after that subtraction, we're going to add that value that we grabbed, that R5, in the case of 1, 2, 3, 4, it'll be the number 1. We're going to say add the immediate value of the result of getting the ASCII character 0, which is going to not default, but it's going to equal 48. So in the case of the number 1, we're saying add 1 plus 48, which is 49. And then we're going to store that byte 49, which if we look at our ASCII table, byte 49 is, or I shouldn't say byte 49, but character 49 is equal to the ASCII value 1. So store the ASCII value 1 into the memory address where we are ultimately storing the string, which we declared would be R1. And then we're going to take that power of 10 multiplier, which in the case of 1, 2, 3, 4 would be 1,000, and we're going to divide that by 10, which will take it down to 100, and then we're going to repeat the loop. And we're just going to keep going through that until we eventually reach the point where we've gone through all of our numbers. And when we've gone through all of our numbers, we're going to jump down to this null byte label. And the null byte is just going to say move into register 5, the immediate value 0. and then add, which is the null byte, and then add that immediate value to the end of our string so that we know where the string should terminate. And then once we have done that, we will exit the loop, we'll pop our registers back off, we'll branch exchange back to the calling function, and we will be done. So that's the roadmap that I have laid out for the code. And again, since I have actually already recorded this entire series, I know that this roadmap is valid. All right, so that's going to wrap it up for part 1. If you made it all the way to the end of the video, thank you so much for watching. And when we come back in part 2, we will get into the actual code. I hope to see you in the next video.